Okay, good morning, everyone. So today we're going to be continuing with our very quick review of what we did in Physics 660. And so a lot of the problems that we deal with are solving Schrodinger's equation. And the gist of that in words is if we have a Hamiltonian that does not depend on time, and we're given the initial state, psi of 0, we want to know what is the state at some later time. So what is the state psi of t? Okay, so we can do this in the following way. It breaks down into 3 steps. Step 1 has nothing to do with what the initial state is. It just has to do with the Hamiltonian. So we want to find the eigenvalues and the eigenvectors of the Hamiltonian. Okay, and so the eigenvalues we call the energies. So it's a list of E numbers, and the corresponding eigenvectors are labeled by that eigenvalue, but they also have some degeneracy label because there can be more than one such state. Okay, then step 2 is you want to write the initial state that you're given, psi of 0, as a linear combination of those eigenstates. So you write a sum over energies. For each energy, you sum over the degeneracy labels, and then you have some constants. That C sub E rho of E is just a list of constants multiplied by the corresponding energy eigenstates. So you know that you can always do that because the eigenstates of this observable, namely the energy, form a basis. And that means any state can always be written as some linear combination of it. And so that's the task in step 2, is to find that linear combination. Then step 3 is basically the easy part. You just write down the answer. So if you've done steps 1 and 2, the solution of Schrodinger's equation can be written down very easily. It's psi of t, the state equals, it looks almost like psi of 0. In fact, it has the same coefficients in it. But now you put an exponential of e to the minus I times the energy times the time divided by h bar times your eigenstates. So each energy eigenstate just gets a different phase, and that's the solution to Schrodinger's differential equation. So that means a lot of times the first thing we want to do, of course, is step 1. We want to find the eigenvalues and eigenvectors of the Hamiltonian. And that's often the hard part. So I want to next go over some of the classic problems in quantum mechanics that we studied in last semester. Starting with number 1 is the particle in a box. So each one of these classic problems is something that that you should sort of have in the back of your mind. So in a particle in a box, you have a box that goes, let's put the origin here, and this is minus L over 2, and this is L over 2. And then if you're outside the box, the potential is infinite. So you're basically forbidden to be in those regions. And if you're inside the box, the potential is 0. Okay, so this is potential. And so wave functions in quantum mechanics are always continuous. And so the wave function at the point L over 2 is going to be 0 because it has to be 0 outside the box. And you're forbidden from being inside the box. And so this problem is one we solved. And so I'm just going to write down, remember what the answer was. The wave functions look like this: square root of 2 over L cosine n pi x over L, where n is an odd integer. And if n is an even integer, you get solutions that look like this: sine n pi x over L again. This is for n equals 2 for 6. N equals 0 doesn't give you a solution, so we don't count that. And then corresponding to those states are energy eigenvalues, which we label by the integer n, and those come out to be h bar squared pi squared n squared over 2m L squared. So if you have a test or something and you've forgotten what these things are, you can reconstruct them just by remembering that, first of all, they're trigonometric functions. And secondly, they have to vanish here and here. And third, they have to obey the differential equation for the Schrodinger equation, which tells you what allowed numbers go there: n times pi divided by the length of the box. And then finally, the square root of 2 over L is just normalization. So now you can draw pictures of what these wave functions look like. So here's our box. And one picture, so the ground state, the n equals 1 state, looks like that. It's just a cosine. For the n equals 2 and n equals 3 states, they look like this. Here's n equals 2. Here's n equals 3. Okay, they're just sines and cosines. And then if you look at the parity, you realize the eigenstates are also of energy are also eigenstates of parity. One of the useful things about knowing the parity state, that these are parity eigenstates, is that then when you're doing matrix elements or inner products, you know that some of them just vanish because of this parity selection rule. So the parity for the state n is, it turns out, -1 to the n plus 1. That just says for n equals 1, for example, that's a parity even eigenstate, which means if you reflect through the midpoint, it's even. This is an odd eigenstate, which means if you reflect through the 0 point, then it's odd. Okay, so that was one classic example. A generalization of that that's a little more complicated is the particle in a square well, which is similar to the particle in a box, except that instead of an infinitely large potential outside the box, the potential is finite. And so let me just draw sort of what the first few wave functions look like. Here I'm drawing my square well. This is the energy V0, and this is the energy 0. And then the wave function for the ground state looks something like this. The energy for the first, or the wave function for the first excited state looks something like this. Okay, and in both cases, if you are outside the well, it's a dying exponential. And if you're inside the well, it's a trigonometric function, either a sine or a cosine. So that goes both for this and for this. But solving this thing, if you may remember, the energies were much more complicated to get than for the particle in a box. These were solutions to a transcendental equation. A transcendental equation, I probably spelled that wrong, is one where you cannot solve for them algebraically, so you solve for them graphically. The nice thing about problems that you can't solve in terms of algebra is that you don't have to solve them because you can't. And the idea behind this, again, was to match the wave function and its first derivative at the boundary of the square wall. That's the key thing that gets you the transcendental equation. Okay, we're actually not going to talk about that particular one further in this class. One that will come up is a harmonic oscillator. This is one of the really great classical examples. Okay, for which the Hamiltonian, remember, looks like p squared over 2m, that's the kinetic energy part, and the potential energy part is 1/2 m omega squared x squared, where omega is the frequency of the harmonic oscillator. So we solved this two different ways in Physics 660. The states, either way, are labeled by an integer n. These are the energy eigenstates, where n this time can be a non-negative integer. So this time n equals 0 is included. Okay, and remember, n equals 0 is not the null ket. And in terms of, so now you can rewrite the Hamiltonian in a different way, which is a dagger a plus 1/2 times h bar omega, where a dagger and a are certain operators that you can define in different ways. One way to define them is just how they act on energy eigenstates. So a dagger acting on n gives you square root of n plus 1 times the state n plus 1. So it raises the energy by one quantum number, and it multiplies by this funny square root factor. And a is a lowering operator, so it has a factor of square root of n, but it lowers the energy by 1 unit. 1 unit meaning h bar omega. Okay, and then directly from this formula for the Hamiltonian, the energy eigenvalue of the state n is h bar omega n plus 1/2. Because you can check that, because if you act with a on n, you get a square root of n. Then it becomes n minus 1, and you act with a dagger on that, and you get another square root of n. And that gives you the n here. And the 1/2 just comes from reducing this original Hamiltonian to the a and a dagger operators. Okay, so then you can write down the wave functions for a given energy eigenstate. I'm not going to write down the general form for this, which you can find in the notes, but I'm just going to comment that they have this form where they are Gaussian functions times polynomials. And in fact, specifically, they are Hermite polynomials. And so just for example, the lowest energy state, the ground state, has this wave function. So first of all, it's by definition the inner product of the position ket x with the ground state ket. There's a normalization factor that turns out to be this, m omega over pi h bar to the 1/4 power. And so that, and then there's a Hermite polynomial, which in this case is just a constant. So it's part of the normalization. And the Gaussian is always of this form. It's the exponential of minus m omega x squared over 2h bar. Okay, so then the wave functions of the excited states look very similar, but you just have some extra polynomial that goes here that gets more and more complicated as you go to higher n. All right. The fourth classic example, classic meaning classic as in famous and everyone should know it rather than classical mechanics, is the hydrogen atom. Okay, for which the Hamiltonian is now in 3 dimensions, p squared over twice the mass of the electron. I'm going to write m sub e for mass of the electron there, minus a Coulomb potential z e squared over r. E is just the charge of the electron in CGS or Gaussian units, which you can find on the first page of the notes. R is the radial position operator. P squared is the momentum squared operator in 3 dimensions. And for hydrogen, z equals 1, but we like to be able to treat ions that have different nuclei. And so we leave it general sometimes, but z equals 1 for hydrogen. Okay, and then we solved this for the eigenstates and the eigenvalues. And the results we got is we found stationary states. Remember, stationary states are just another way of saying energy eigenstates. The energies are labeled by an integer n, and they look like this. So first of all, there's a minus sign. The minus sign is telling you that these are bound states. They have negative energy compared to the energy that the electron would have if it were very far from the origin. And then there's a factor that you can write in several different ways. Let me write it this way first. E to the 4th mass of the electron over 2 h bar squared. And then there's a factor of z squared over n squared. So there are several ways to think about what this prefactor is. First of all, numerically, this prefactor is given a special name. It's a unit of energy, and this is 1 Rydberg, which is famously approximately equal to 13.6 electron volts. So that's a number that every physicist should know. What's the bound state energy of the ground state of hydrogen? And so one way of thinking about why does it have to have this form that it does? So first of all, it's got a mass of the electron in the numerator. So the reason why that should be there is, let's say you were in the limit where the electron was very, very heavy. If the electron's very, very heavy, then it's got a lot of inertia, and so it can't escape from the nucleus very much. And so it should be closer to the nucleus. And if it's closer to the nucleus, then it will have a very attractive bound energy. And so sure enough, the energy is proportional to minus the mass of the electron. In the same way, if the electron charge is larger, this is also the charge on the proton, by the way, but if this is larger, then again, the electron is going to be closer to the nucleus, and so the bound state energy will be larger. So that's how telling you it's proportional to a positive power of E, and it happens to be e to the 4th. And then it's inversely proportional to h bar. And one way of thinking about that is, again, the very first thing we did in the notes was to notice that classically, the classically charged matter is unstable. The electron will just fall into the proton and nothing can stop it. So in reality, what's stopping it is quantum mechanics, and the classical limit is where you take h bar goes to 0. And so this is saying, if you were to take h bar goes to 0, the bound state energy should go to -infinity, which is indeed what happens. Okay, so in any case, that's the energy we solved that without resorting to any hand waving. And then you can label the energy eigenstates by 3 numbers. The first number is a positive integer. That's nothing other than the integer n that labels these e's. Okay, and that's often called the principal quantum number. Principal meaning the main one. But then for each n, you can have different angular momenta. And the different angular momenta you can have are 0 up to n minus 1 in units of h bar. So this is angular momentum. And then for each of those values of angular momentum, you can have a different z component, which is labeled by another integer m. M can run from minus L up to L, and this is often called the magnetic quantum number. And those three numbers together correspond to a complete set of commuting observables. Namely, the complete set of commuting observables H, L squared, and L sub z, and the corresponding kets are labeled N, L, M. But their energies only depend on n here. And this is the formula that each one of these states has. Right, but just to, again, make sure we understand what the notation means. The notation means if you act with the Hamiltonian on one of these energy eigenstates, you get back the number E sub n times the same state. If you act with L squared, okay, you get H bar squared times L plus 1. The key thing to remember there is that it's not L squared, it's L times L plus 1 for the eigenvalue. And then if you act with L sub z, you get back H bar times M times the same ket. Okay, and so these are simultaneous eigenkets of these three operators, which therefore form a complete set of commuting observables. Okay, so those are the kets, and then given the kets, you can work out what are the wave functions. When we solved the hydrogen atom, we actually did this simultaneously with finding the energy eigenvalues. So they are as functions of the spherical coordinates r, theta, and phi. They split up into a radial part, which only depends on n and L, not m, and a angular part, which only depends on L and M, but not N. Okay, so they both happen to depend on L, but one of them doesn't depend on M, and it only depends on radial. And the other one here is the spherical part. Those are known as the spherical harmonics. And that part of the problem, it's not special that we're talking about the hydrogen atom. Any spherically symmetric potential that we deal with is going to have the same spherical harmonics. That part will be independent. It's really this part, the radial part, that depends on the particular potential we're talking about. So in the notes, you can find a solution that we found for the radial wave function. I'm not going to rewrite it, but I'm just going to write exactly, but I'm going to write it sort of more schematically. These functions have the following form. There's some horribly ugly constant that I can certainly never remember, but that's just there to have it be normalized. Then there's an exponential part, which looks something like this. Okay, and so A0, I need to tell you what that is. A0 is, remember, the Bohr radius. It's just a particular combination of the things in the Hamiltonian that has units of length. And so it's equal to h bar squared over e squared m sub e. And numerically, that turns out to be 5.3 times 10 to the minus 11 meters. Okay, so going back to the formula up here, we have this exponential part. There's also a part, and notice the exponential part depends on n. There's also a part that goes like r to the L power, and I'm going to write that like this, r over n a0. A0 is the Bohr radius. That's to the L power. And then multiplying that are a bunch of polynomials, associated Laguerre polynomials, it turns out. And so a general thing that one wants to do when solving problems like this is reduce the problem to solving for some polynomials. That's what happened in the harmonic oscillator, and that's what happens here too. Okay, so this exponential part here is really reminding you that you have an attractive force. This is telling you the electron is attracted to the proton or the nucleus and it wants to be close to it. That's why it gets smaller exponentially. But counteracting that is a centrifugal effect. So notice that for larger angular momentum L, this factor is telling you that your electron wants to be further from the proton or the nucleus. And then the associated Laguerre polynomials here are really telling you about radial excitations. So the larger n is, the more wiggles the associated Laguerre polynomials have, and the more wiggles it has, the more kinetic energy the electron has. Okay, so that's sort of the schematic form of the radial wave function. You can also rewrite one Rydberg. I said there was more than one way to write it. So another way of writing it is it's e squared over twice the Bohr radius, which has units of energy. And yet another way of writing it is 1/2 the mass of the electron times the speed of light squared times alpha squared, where alpha is another number that we're going to mention quite a bit in this class. It's e squared over h bar times c. It's very famously 1 over 137.036 something, something, something. At one point in history, people thought it might be exactly 1 over 137 for some deep reason. And famous physicists even wrote papers trying to explain why it would be exactly 1 over 137. And then they discovered it wasn't exactly 1 over 137. Okay, so this is fine structure constant. Okay, and so what this is saying is Einstein's famous formula equals mc squared would give you this part. Okay, but that's a very large energy. And then the alpha squared is saying, due to the velocity of the electron, there's a very small number that gets squared that multiplies that to give you the actual energy. Okay, so for the ground state's a particularly useful example of this. For the ground state, the associated Laguerre polynomial is just a constant. There is no L factor because L is 0. In fact, there's only one state, and it just works out to be this: 1 over square root of pi a0 cubed times the exponential. Okay, so everyone should remember that the ground state of the hydrogen atom looks like an exponential that's falling off. And then if you forget this part, you can always reconstruct it by just requiring that the state be normalized when you integrate over all space. All right. Another important feature of the hydrogen atom is the degeneracy. of the energy level n. Okay, so our notation for degeneracy is a small letter g. I don't know why, it just is. But so this means the degeneracy of the level n. That means how many states there are with that level. And you get that by summing over all the other quantum numbers. So we're going to sum over L equals 0 to n minus 1, because if you go back up here, right, those were the allowed values for it. And then we also are summing for each L, we're summing over the allowed values of M, which means M equals minus L to L. And for each one of those quantum numbers, there was one state. So I'm putting a factor of 1 here. Right, and if you just count up, how many are there from minus L to L? There are 2L plus 1 of those. And so for the rest of this, we're really adding up what are the first n odd numbers. And it turns out the first n odd numbers, when you add them up, gives n squared. So that's naively the degeneracy of each energy level of the hydrogen atom. The higher you go in energy, the more degenerate they become. But actually, we've left off an important part, namely spin. And so you actually have to multiply this by a factor of 2 for the electron spin, and another factor of 2 because the proton has a spin. So this is electron spin. This is the proton spin. That's assuming it really is hydrogen. If it's some other nucleus with a different value of Z, then you have to look up what is the spin of that nucleus. There are some nuclei that don't have any spin. There are other nuclei that have some different spin that's not 1/2. So these factors of 2 are because they're spin 1/2, so they're either spin up or spin down. And then there's our factor of n squared that we've already figured out. And so in reality, the hydrogen atom has a degeneracy of 4n squared at the level n. So in last semester, that's sort of where we left things. But in this semester, we're going to realize that's not quite true, because the degeneracy is partly broken by relativistic effects. And these relativistic effects are broken down traditionally into 3 types. There's one part that's called the fine structure. The fine structure actually itself breaks down into several subparts the way we usually analyze it. Then there's something called the hyperfine, which has to do with the nuclear spin. And then there's a third thing called the Lamb shift. Okay, and so we will talk about all 3 of those and figure out what they do to the, they give small effects to the energy of the hydrogen atom and partly break this 4n squared degeneracy, but they don't completely break it because there's still a rotational invariance that says there's no special direction. And so it's something we have to think about is, how does this degeneracy in M get broken? And so the answer is that it gets partly broken. Okay, maybe I should pause here and see if there are any questions on anything we've said so far. I sort of reviewed now all the classic problems that we learned in last semester. No? Okay. So then the last major topic we had last semester had to do with angular momentum. And so there are different ways to think about it. One way we thought about it is just in terms of orbital angular momentum. But more generally, you can think of angular momentum as just some set of three operators that satisfy some commutation relations. And so they look like this. There's a Jx and a Jy, and if you compute their commutator, you get I h bar, J sub z, and then there are three permutations of that because you can take the commutator of Jx and Jz or Jy and Jz. Okay, so I'll just write and permutations. Okay, and just from that alone, we were able to work out how to label the eigenstates of angular momentum. And the answer is you can label the states by two numbers, J and M, that correspond to the total angular momentum squared, which is Jx squared plus Jy squared plus Jz squared, or otherwise known as the vector J dotted into itself. And then M is for the Z component. Okay, and that's if you have one particle that has some angular momentum that you're calling J. That J includes both the orbital angular momentum associated with the movement of the particle itself and the spin of it. But then a lot of times we're going to be interested, for example, in the case of the hydrogen atom, we have an electron spin and a proton spin. So what happens if we have two particles? And so for two angular momenta, a complete set of commuting observables is the following. First of all, I can have the total angular momentum of particle 1 squared and its Z component, and the total angular momentum of particle 2 squared and its Z component. So that's just treating the two particles as if they were completely separate things and never interacting. And that is called the product basis, or the basis that you get from that complete set of commuting observables is called the product basis. Okay, and the product basis can be labeled like this: J1, J2, M1, M2. But a lot of times that's too much to write, and we get lazy, and so we just leave off the J1 and J2 because maybe they're fixed, or we're going to treat them as fixed. And so we might just write M1, M2. And because those are two numbers, I will often put a colon between them. This is not a standard notation. This is something that I like to use, so it's in the notes. But you shouldn't expect to see this in other books. Okay, and so J1 squared, for example, acting on this ket, or one of the kets of this form, just gives you back h bar squared J1, J1 plus 1 times the same ket. And here I've written it in the first notation, right? But so all this is saying is that J1 squared only cares about that quantum number. It just ignores the other ones and gives you back what you would have gotten if particle 2 didn't even exist. Okay, and so I should say maybe etc., because you can sort of do the obvious thing with all the other operators. So what is the product basis good for? Two things. One is it's just the natural, it's the natural basis in which to write down eigenstates for two particles, but also it's useful because, for example, J1Z and J2Z and J1Z plus J2Z are diagonal in this basis. What do I mean by that? It's really the same thing as just saying the kets in this basis are eigenstates already of each one of these three operators. And so when you act on them on an eigenket, you get back the same eigenket. That's the same thing as saying that you have a diagonal matrix. So one of the reasons that's important is a lot of times in quantum mechanics, when we're solving a problem, the whole thing we're trying to do is we're trying to find a basis in which important operators are diagonal. And so, for example, let's say your Hamiltonian had a magnetic field, B. And so if your Hamiltonian had a magnetic field, B, that happened to be interacting with J1, right? And if B is pointing in, it has to be pointing in some direction. If it's pointing in the Z direction, this is going to be B times J1Z. If that's a term in the Hamiltonian, you want to choose a basis where that's diagonal, and that's what the product basis does for you. Okay, but not all problems are like that. And so there is also the total angular momentum basis, which is a different basis. And here the complete set of commuting observables is J1 squared, J2 squared, but now the total J squared and the total JZ. Okay, so first of all, J, the total J is equal to the vector sum of the J1 and J2 operators. And so now the eigenkets of this complete set of commuting observables are labeled J1, J2, J and M. Or if we're being lazy, we can just write J and M. If J1 and J2 are considered to be fixed, or we're treating them as fixed for the moment. Okay, and notice that in this case, because there are two numbers here and there are two numbers here, my own personal way of telling the difference is I don't put a colon. Sometimes it's just obvious. For example, if I'm writing J and M, then it's just obvious by the fact that I've written J and M that I'm not talking about M1 and M2. But if I wrote here, say, 2 and 0, then it might not be so obvious which one is which. So now here's a very important trick for dealing with a total angular momentum basis, is the fact that if you look at J1 dot J2, you can write that by taking this and squaring it out. You can rewrite this as 1/2 J squared minus J1 squared minus J2 squared. This is an extremely famous and useful trick. And if you're working in a problem and you see the dot product of two angular momenta, then it's very likely, it's not completely certain, but it's very likely that you should be using this trick. Why is this useful? It's because now acting on the kets in this basis, this is just a number instead of an operator. It's 1/2 H bar squared J times J plus 1 minus J1, J1 plus 1 minus J2, J2 plus 1. So again, a standard trick in quantum mechanics is you want to turn operators into numbers. How do you do that? You go to a basis where the operators are diagonal, and where your kets, your basis kets, are just eigenkets of those operators. And so that's what this trick does for you. So the thing to remember is you see a dot product of angular momenta, you rewrite it like this, and then you turn it into numbers. And you don't forget that J squared is not little j squared, it's little j times little j plus 1. Okay, so this is a basis. Your diagonal, this operator is diagonal in the total J basis. And so if you see that operator, or if that operator is very important for you, that's the basis you want to use. Okay, so I'll just write this again. I've already said it in words, but if J1 and J2 are fixed by context, by, for example, the statement of whatever problem you're doing, then M1, M2, then we write them like this with a colon and JM. So this is the product basis, and this is the total basis. But in many cases, the problem is you have one basis that you're given and you want to translate into the other basis. Okay, so we want to, so a problem that commonly arises is we want to trade these or go from one to the other, write states in one basis in terms of states in the other basis. So the good thing is that because of the theorems we proved, we know that that can always be done. We know that a ket JM in the total basis, for example, is some linear combination of kets in the product basis. So let's just write that down. There's a sum over all M1s and a sum over all M2s of those kets in the product basis. And then completeness even tells us how to compute those. Namely, we have to compute these inner products. And those inner products are given a special name because they're so important and useful. These are the Clebsch-Gordon coefficients. Okay, and one thing we did last semester was figure out how to compute them. They are chosen real by a convention. And we have a notation for them that, again, is not completely standard. Some books use this. J1, J2, J, M1, M2, M. Okay, so it's just a bunch of coefficients. Many of them might vanish because there are selection rules that tell you some of them, sometimes they vanish. But if you found them, a great thing is then the inverse thing is also available to you. M1, M2 is some linear combination of total angular momentum states. So we know that we can write a sum over all the J's that could possibly be there, which is J1 minus J2 up to J1 plus J2. And then a sum over all the M's. That's the total magnetic quantum number times kets Jm. And then again, completeness tells us that these are the coefficients. And because we chose a convention where they're real, this would normally be the complex conjugate of that, but because they're real, they're just equal to each other. So the Clebsch-Gordon coefficients are also these combinations. Either one is just as good. Okay, and then last semester, we figured out how to figure out what those coefficients were. There's an algorithm for computing them, which I will not review. Okay, but it's based on the following principle, that you act with the operator J minus, which is equal to the sum J1 minus plus J2 minus. And so this is a lowering operator for angular momentum. You could also use the raising operators, you'll get the same answer. Okay, but it's all based on the following fact that J minus acting on an eigenket gives you back the following: H bar square root of J plus M, J minus M plus 1, and it lowers the magnetic quantum number by 1 unit. And by the way, you can rewrite this as J times J plus 1 minus M times M minus 1 in the square root. Okay, so this lowers the magnetic quantum number. Okay, and so the whole strategy is based on the following fact. You first do it in the product basis, Then each of these operators you evaluate in the, sorry, this you do in the total angular momentum basis. These two you do in the product basis. You require that the results you get are the same. That gives you a big set of equations, and you solve the big set of equations, and you're done. Okay. Oh, the one other thing you need besides that is orthonormality. So you use the fact that these are assumed to be an orthonormal basis. Actually, they're not assumed, they're guaranteed by the theorems we proved. And that gives you can solve for all Clebsch-Gordon coefficients for a given fixed J1 and J2. Okay, the other method, of course, is that people have compiled big tables of these. And for example, Mathematica and probably Python too. I haven't tried it in Python, but probably there are many computer programs that will just have these things built into them. The only thing you have to be careful of is, even though everyone agrees that these things should be chosen real, there are still some different conventions that people use for what these coefficients are that are physically equivalent, but they'll give you different numbers. And so if you're mixing and matching different sources, you might have problems. Okay, so that is it for today. And it's also the end of our very quick 2-day review of everything we did last semester. Of course, we can't review everything we did last semester, but this was our approximation of that. And so next time, we're going to be talking a little bit more about addition of angular momentum. And then we will be going into the topic of perturbation theory, which is an approximation method for solving problems. Okay, as far as I know, we are going to be meeting in person on Monday, but I've been told that the university will possibly make an announcement on Sunday afternoon about what the COVID rate is and what they're going to do. So the short answer is I'm not completely sure, but I think, the best of my knowledge, we'll be meeting in person on Monday. All right, are there any questions for today? All right, if not, I will hopefully see you Monday.